So this presentation is going to be on bonding. So you should pick up in your notes on page 2 on the top. You should see a guy that looks like he's striped on that page. So what we're going to be looking at is, first we'll look at the 6 elements most commonly found in living things, and then we're going to do a broad overview of bonding. Why does it occur? What are the different types? And then even within one of our types, so covalent bonds, there are some subtypes that become really important when we consider how the role they play in nature. So we want to know those as well. The first thing we need to do is that when we look at living matter, so the stuff that makes up living things, we find that there are 6 elements that make up over 90% and 98% of all living matter. So I want you to think right now, see if you can figure out what some of these might be. So maybe you got a few of these. So the acronym we want to use to remember this is CHNOPS, CHNOPS. And it's a silly non-word, but it'll help you to remember these 6 elements. Now, this is a straight memorization task. You can use the acronym to help you, but like the levels of the taxa, it's just one of those things we need to commit to memory. So the C is for carbon, which is super important. The element carbon is what gives us all of our organic matter. Then we have hydrogen, which we often find bonded to carbon. Nitrogen is our N, O for oxygen, P for phosphorus, and S for sulfur. Now, we're going to talk about how these elements are arranged together in some of our complex organic molecules, and we'll see these again. We'll talk about them a lot in our next unit. And then there's our guy right there, of what we're made up of in terms of each of these elements. So pause here and make sure you have these down in your notes. All right. On MCAS, which is something we know is coming up in June for us, there's always one question about CHOPS on MCAS. They just like to ask a question about this every single year. And again, it's one of those straight memorization tasks. If you know you're talking about something that's living, then you should apply CHNOPS to it. So take a look. Question number 41 is going to be our first one on the left. Which of the following lists of elements contain the most common elements in organic compounds? Good. So we should have seen that B gives us carbon, hydrogen, and oxygen, which is the CHO of CHNOPS. So that is the answer there. But sometimes they like to get a little tricky. They'll give you a molecule you might not be familiar with. You don't need to know the structure of the molecule. You just need to know it's found in living things. So try 17. Vitamin D is an organic molecule that regulates the absorption of calcium in the body, so found in a living thing. Which of the following elements is most common in a molecule of vitamin D? Good. So hopefully you got B, carbon. Since we're talking about organic molecules, we're talking about CHNOPS. So what we're going to do now is really focus on bonding. So we're going to look at how these elements, how these small particles that make up all living things, make up all things, including all living things, interact with one another. And in order to understand the structure of an atom and how they interact, we just need to remember a basic rule we learned in elementary school while we were playing with magnets. And that is that opposites attract and like charges repel. So we know atoms are made up of charged subatomic particles. We can understand the interactions between these subatomic particles, both within an atom itself and between different atoms, if we remember this basic rule. If things have opposite charges, so a plus and a minus, those things are going to attract. They're going to want to be near each other. Whereas 2 pluses are not going to want to be near each other. So 2 positively charged things and 2 negatively or minus charged things will not want to be near each other. They will repel. Why atoms bond? So atoms want to fulfill what's known as the octet rule. Now, oct, if you are familiar with geometry, your octagon, oct means 8. So atoms want to have 8 electrons in their outer shell. This outer shell is also been referred to as the valence shell, so VALENCE. So it's also called the valence shell of an atom. And they want to have 8 electrons in there. This allows the atom to be in its most stable form, and that's what atoms are essentially seeking. So what they're going to do is they'll play a little electron exchange game in order to get to this stable position. They'll share them, they'll give them away, and that's what bonding is. It's atoms trying to fulfill this octet rule to become as stable as they can be. Now we notice that in our picture of argon that we see on our right-hand side, we have that nice blue circle in the middle that's representing our nucleus. I have a nice plus charge there because that's where we find our protons, our positively charged subatomic particles. Around that, we notice there are 3 rings. Those rings are called orbitals. Electrons are negatively charged, and they are all negatively charged. So do your electrons like to hang out very close to each other? No. They're going to try and get as far away from each other as they can because they're going to repel. So we find that they have specific positions they're going to take up around the nucleus of an atom because it's pretty much as close to each other as they can stand to be while still trying to get close to that oppositely charged positive nucleus. So our first ring or shell gets 2 electrons, our next gets 8, and our third gets 8 as well. There are orbitals outside of these that we will learn about in chemistry, but not in biology. I'm only going to hold you responsible for knowing that it is 2, 8, 8. So what they want to do is they want a full shell on the outside. Now, for some small elements, for example, hydrogen only has 1 electron, so it only gets 1 in that first shell. Hydrogen's an easy one to please because all it needs is to either share or steal 1 electron in order to be happy, to have its 2 electrons on its full shell. But they're trying to reach these numbers, this 2, 8, 8, to fill one of those shells in order to be stable. So the first way they can get about this stability, so fulfilling those octet rules, filling up those shells with electrons, is they can share them. And that's what a covalent bond is. The easy way to remember this is co. Co as a prefix means together. For example, you might have a co-teacher in one of your classes, 2 people teaching together. In a covalent bond, what's going to happen is we have 2 atoms that their nucleus is strong enough. So there's enough plus charges in the center that their electrons like them. They want to hang out around that plus charged nucleus in the center of that atom. So what they're going to do is they won't let go of their electrons, but they will share them. So these atoms will get very, very close to each other, pretty much as close as they can stand while their positively charged nucleuses are repelling each other, and they'll share some electrons in their orbitals. And we'll kind of look at what this looks like. So a lot of times when it's drawn, it's just drawn as an electron that's sitting in between their 2 orbitals. But essentially what it is this is an electron that essentially skates a figure 8 around these nucleus. It's going to hop back and forth between the 2 atoms, making both stable. So the electrons, because they're negative, they're attracted to the positively charged proton, but neither of these atoms are going to let go of their electrons. They have to share them. There are 2 types of covalent bonds, so 2 types of electron sharing we see in atoms. The first type is called a non-polar covalent bond. In this one, an atom in a molecule is going to share electrons evenly. So that means neither nucleus is positive enough to attract an electron any more strongly than the other. So the electron spends an equal amount of time with each atom. It's sharing itself evenly between them. Carbon dioxide, CO2, is an example of a nonpolar covalent bond. This makes CO2 very, very stable. It's very non-reactive, which is why fire extinguishers are often filled with CO2, because you can spray it on a fire and it won't combust. It's not going to add any more because it's super stable. CO2 likes itself. It's happy with who it is. It doesn't need to bond or react with anyone else. The weird analogy I always think of for nonpolar covalent bonds is it's like if you imagine the nucleus in the center, so that strong positive force as being like a person. What we have here is nonpolar covalent bonds formed between 2 atoms that have equally strong nuclei. So it would be like a tug of war with an electron between equally strong men. So if they tug and tug and tug, it might one time spend a little more time with this one, another time spend a little more time with that one, but it's being evenly shared between them. So it's an even sharing. We can contrast that with polar covalent bonds. This is the opposite. They're still sharing the electron. It still hops back and forth between both of the nuclei, but it's not being shared evenly. It's spending more of its time with one atom than it is with the other. So the nucleus of one atom is pulling harder, meaning that it has more positive charges, more protons in the center, so the electron just likes it a little bit better than it likes the other one. Classic example of a polar covalent bond is water. So when we look at oxygen, oxygen has 8 protons in its nucleus, so 8 positive pieces that are pulling on these negative electrons. Hydrogen, measly little hydrogen, has 1 proton, just 1 positive thing that's pulling on these electrons. So who do the electrons like better? They love oxygen because it's got all that positive that they want to go hang out around. So your electrons are going to spend more time around the oxygen, making the oxygen act negative. Since they're spending less time around hydrogen, hydrogen's going to act positive. Notice that it is a partial, so that nice figure 80 symbol, that means partial charge, because oxygen's not stealing the electron, it's just spending more time with it. So it's still covalent, still sharing.